Hi, yet another important video from the course Electronic Devices and Circuits. Some important derivations and final conclusion, some pictures and derivation. The video may be lengthy, but stay with me. Let's reach to that point where we have to go. Alright, a full wave rectifier, some discussions regarding a full wave rectifier, and probably expression for a ripple factor of some filter. Alright, let's see what it is. A full wave rectifier. From the beginning, the picture, we have a step down transformer, and make sure you draw that, you show that difference in the picture. It's a step down transformer which we make use of in rectifiers. Step down, alright. Number of turns are more over here, number of turns are less. That should be shown in the picture itself. Alright, so this we have, right, and even this, and that confusing point is for a student, exam point of view, for a student, they do some mistakes and which you have to avoid. We have the cathode over here, another cathode of D1 and D2. These two are joined together, and from the common point we introduce a load resistance. Alright, so that's one, and it's incomplete. We have a center tapping for a full wave rectifier with the two diodes. This in order to avoid this center tapping, 4 diodes are used. Bridge rectifier, also a full wave rectifier, second classification of full wave rectifier. Alright, so for the time being this one. Alright, and simply hanging the diode in air or just plugging it on a breadboard and asking it to do the rectification, that the diode alone cannot do that, isn't it? So we need to make use of some other components, and then the rectification is done. Like what? This will be the input, and finally we need a straight line which is a DC AC input, and we need to have this one. Alright, that cannot be this waveform cannot be converted to this at a snap in one step, but it's stage wise. First stage something else, second stage something else, some other modification, finally then we go for it. We have number of stages to in between that conversion, this waveform to this waveform. Alright, and yeah, and what the inherent property of a transformer, like we have point A and point B. The property of transformer, the construction and the working is in such a way that when this is positive, at the same instant B, this point will be negative, and vice versa. When this is negative, at the same point B will be at positive. Now this property of the transformer is made used in rectification process. Alright, why? Because guys, let's discuss. If it is positive and negative, guys, positive to anode of D1 and negative to anode of D2, which one will be forward biased? This one. This is forward biased and reverse biased, so this doesn't exist anymore. Now it's a closed circuit, and the current will be flowing from anode to cathode. See, current will be flowing from anode to cathode. Alright, so extent, we don't have this anymore. It's open, so we don't have this anymore. It's a closed circuit. Alright, so current is flowing in this direction, current is flowing in this direction. Remember this direction when A is at positive potential. Alright, so this is the direction. Alright, and the second case, reconstructing the circuit, we have that second diode over here. Alright, and this is the construction. And the second case, what? When A is negative and B is positive. Right, and D2, positive to anode of D2, negative to anode of D2. Which one is forward bias and which one is reverse bias? This is forward bias, conduction takes place to this one, and this is off. We don't have this anymore. And current in the circuit, closed loop, will be flowing from anode to cathode. So these are direction of this one. So this, it's open, so no chance of going that side, this side, and the current will be flowing in this direction. See, even for the first half cycle, current is flowing in this direction. Even for the second half cycle, current is flowing in this direction. Alright, here it's a bidirectional, this side and this side, but at the end, at the low resistance, we have a unidirectional signal. First here and second one here. So this is how rectification is done. And so what will be the corresponding waveforms? It's like this one. This will be the input. Alright, be careful. We are not obtaining any time scaling or amplitude scaling or anything else. Only the rectification is done. Alright, diode 1 this will be on, diode 2, this will be on, diode 1, again this one, diode 2, this one. Right, for the derivation purpose, guys, one thing to be clear over here. What is it? It's a 0, it's a pi, a 2 pi, 3 pi, and 4 pi for the output load current and load voltages. Output voltage and load current. Alright, so this will be the load resistance RL. Right, and another question, every human being has a sixth sense, a common sense, and that has to work at some times, isn't it? So give me an answer. From which time period to which time period is one cycle? It's here, it's 0, pi and 2 pi. 0 to 2 pi is one cycle, because this is repeating after, this waveform is repeating after this. Alright, so coming to this one, output from the rectifier, what's the side, from which point to which point is the one complete cycle? It's 0 to pi, isn't it? It's 0 to pi. Why? Because this is repeating, again, this is repeating. Alright, so we'll make use of this one to evaluate some important terms. Alright, so, and it's complete AC, right? Underline this one, it's complete AC. And this is, which is known as a pulsating DC. Pulsating DC is a combination of AC and DC. This is known as pulsating DC. Alright, pulsating DC. It's a combination of AC and DC. So that procedure, so what to do if to find out if what amount of DC is existing and what amount of AC is existing. The main motive of rectifier is AC should be converted to DC. We didn't get this one yet. We have to wait for something. We have to do something else to get this one. Alright. So for the time being, from the circuit, this is the output. Alright. This is the output, and it's a combination of AC and DC. It's not a straight line. It's neither straight line nor a perfect sine wave. It's a pulsating DC, which is a combination of AC and DC. Now the task is to find out what amount of AC and what amount of DC is existing in the pulsating DC. Alright, so the average value, will give us whatever, thinking this to be load current, IL, alright, IL, this will be the maximum current, IM, this point. Alright, so the average of the waveform will give us the average value, which is the DC value. The RMS of this waveform will give us the amount of AC in that waveform. Alright, now this next step, how to evaluate average current, which gives us IDC. We have a formula for that, which we follow during the whatever rectifier circuits we make use of. It's a area under the curve upon base, average or base. Alright, what is the base? So evaluating IDC, isn't it? It's a base, this is the base, it's a pi. Alright, 1 by pi, which is the base. And how to evaluate the area under the curve? It's integration 0 to pi for what? Load current IL d theta. And what it is? It's a load current IL, which is equal to Im sine theta, the mathematical representation of this one, right? So we have for each and every shape, we have a mathematical expression. Even this one, it's a Im sine theta, load current will be. So plugging in that value, 1 upon pi, integral 0 to pi, alright. What is IL? It's a Im sine theta d theta. Alright, so this is a constant value that has got nothing to do inside the integration. So we have Im by pi, integral 0 to pi sine theta d theta. So Im by pi as it is. Alright, no change in that one. What do we have? Integral sine theta, it's a minus cos theta, and the limits are 0 to pi. Just plugging in the values, what we have, minus Im by pi, upper value cos pi, right? It's a minus 1. minus cos 0, it's a 1. Alright, so final that product will be, we have a negative over here, minus 2, this negative into this negative, that is positive 2 Im by pi. Alright, this is the amount of DC current existing in the pulsating DC. So what is that? IDC, I average or IDC is equal to 2 Im by pi. Alright, what is that formula? Area under the curve upon base will give us the DC current which is existing in the pulsating DC. Alright, so the next parameter, important parameter to be evaluated is what amount of AC is existing in the pulsating DC. Alright, so what amount of AC is existing in the DC, that is given by IRMS. When we evaluate IRMS, the RMS value of this current, that will give us the AC component, AC which is still existing in the output. Alright, so how to evaluate that one? We have a formula for that one also. What do you mean by RMS? Root mean square, isn't it? Root mean square. Alright, so here this is for the root. Alright, we'll carry out with the root. And square for what? It's we have mean in the sense 1 by pi, isn't it? And integral 0 to pi and IL square d theta will give us the RMS value. Alright, so we have that root. I'm not doing anything with the root. Alright, it's a 1 upon pi integral 0 to pi. Load current is this one, and Im has got nothing to do inside the integration, so I'm taking it out. Im square, where did that square come from? Here, this is square, this is the square. Alright, and sine square theta d theta. Now going ahead, this sine square theta, trigonometric conversion, that should be converted to cos theta. Alright, that root exists. We have that root mean square, isn't it? That root is existing. It's a Im square upon pi. Alright, and integral 0 to pi 1 minus cos 2 theta by 2. Right, and d theta. Don't get confused. That by 2 I have written it outside. Don't get confused. And we are evaluating for IRMS, which is equal to that root exists. That root is still existing. It's a Im square by 2 pi. Alright, 2 pi integral 0 to pi d theta for this. Alright, so here you need to have a clarity. For a backbencher like me, this integral is applicable to this one minus this one. So I am doing that one. 1 d theta minus integral 0 to pi cos 2 theta d theta. Integral cos 2 theta d theta, that will be in terms of sine, isn't it? Integral cos theta, it's a sine theta. Integral cos 2 theta d theta, that will be sine 2 theta by 2. But thing is, this integration will be in terms of sine, and the limits of integrations are 0 and pi. So sine pi, that's 0. Sine 0, lower limit, even that's 0. So this is insignificant over here. We'll carry out only with this one. Alright, and we have that root. We have that root, and it's Im square by 2 pi. And here, what simplification do we have here? Integral d theta, it's that will be pi. That will be theta with the limit 0 to pi. Alright, so plugging in the upper limit is pi minus 0. So we'll have pi over here. Alright, simply we'll have, what do we have? We have pi. And in that case, this pi and this gets cancelled, and finally this root and square gets cancelled. We'll be left with under root 2, isn't it? Im by root 2. Alright, so this gives us the value of IRMS. Right, it's 1 by root 2 times Im, and it's 2Im by pi. Alright guys, so this is the proof. Not only this one, there is something else. There is something else to be found out. And listen, that statement which will be used in the further when the analysis comes to that of filters. What did we have here? What did we have? We have current. Alright, we have current, and the RMS value of this current is this current by root 2 for a full wave rectifier. Alright, if you were in my life, like if we would have been in the class, I would have asked you to write down this statement. We have current. Alright, this has become AC because it's multiplied with sine theta. Alright, so we have current. So evaluating the RMS value of the current, this is to be noted, evaluating the RMS value of the current is nothing but the RMS value of this one is this value by root 2. Right, now another point to be focused is, what is that value? We have 1 time Im sin theta, and the RMS value is 1 time Im by root 2. Alright, we have a reason for that one. What stupid is he talking? No, I'm not talking stupid. There is a reason for that. That cannot be like, okay, when we that comes to the picture, that comes to the discussion when we evaluate the ripple factor for filters. Alright, so yeah, once again I repeat, we have current, alright, IL, which is equal to 1 times Im sin theta. So the RMS value of this one, IRMS, is equal to, what is that? Let me write over here. IRMS is equal to this value Im by root 2. Alright, if we it's a 1 here and 1 has appeared over here. If we would have had something like 6 by 5, the same thing, 6 by 5 appears over there, 6 by 5 times Im appears over there by root 2. Alright, if we would have had IL is equal to 500 by 8 sum Im sin theta, and even that case IRMS would have been 500 by 8 Im by root 2. Whatever here, whatever value or whatever times of Im we have, that will be by root 2 if we evaluate the RMS value for a full wave rectifier. Remember this one. Alright, so what is that? IRMS is equal to Im by root 2. Whatever suffix we have for Im, that comes down as it is, this one. Okay, this is the third time I am repeating. Why? Because in some analysis this discussion comes into the picture, believe me, and another parameter to be evaluated. Right, no, what is the main motive over here? AC to be converted to DC. Alright, AC is to be converted to DC. Now there is something which we have to derive and even talk more about that. What is efficiency? Efficiency is the ratio between output to input. Here we are evaluating output power to the input power. PDC by PAC. Alright, PDC by PAC. Here it's PDC in the sense VDC into IDC. Alright, and in terms of current VDC, it's a IDC RL into IDC. Alright, so that will be IDC square RL, power is equal to I square R, isn't it? So in the same way, PAC will be equal to I RMS square RL. Alright, and efficiency from that one, what do we have? It's a IDC square RL by IRMS square RL. RL gets cancelled, plugging in the values of IDC and IRMS which we obtained there. It's for IRMS, I'm sorry, IRMS. Alright, it's so IDC, it's 4 Im square by pi square square, we have that square, all right, into IRMS square is that goes upside down. It's a square. When we square this one, that square, this root gets away, so we have 2 by IM square, all right. So something gets cancelled here. It's a 8 by pi square. It should be 0.81 something like that in your calculators, all right. So this is for the efficiency. And what is percentage efficiency? It's 0.81 into 100, that will be 81% efficiency. What do you extract from here? Efficiency is 81%, isn't it? So what it says, what that value says. Our aim, the main motive to construct a rectifier circuit is that whatever AC is, it should be converted to DC. 100% give this much of AC, this much of the complete AC to be converted to DC. All right, 100% conversion is required, but only 81% of AC is converted to DC. That's what it's a PDC by PAC is equal to 81%, right? PDC by PAC is equal to 81%. What it is? So PDC is 81% of PAC, only 81%. Okay, better performance than half-wave rectifier. For a half-wave rectifier, it will be only some 40% like that, 40.5, 40.6% like that. But this one, so 81% efficiency is 81%. It says 81% of AC is converted to DC for this full-wave rectifier. All right, this one efficiency is 81. And on the other hand, there is something else to be evaluated. It's a ripple factor. This is how we denote a ripple factor. What that says, the pulsating DC is a combination of AC and DC. So with the ripple factor, we predict what amount of which amount is more dominating. Let's see. A ripple factor, the definition is I AC RMS upon IDC. All right. So something new, is that from another planet? No, this isn't a rocket science. We have a formula for that one, IAC RMS. It's a under root I RMS square minus IDC square, that gives us this one, upon IDC. All right, can this be written as this? Yeah, of course, that gets cancelled and we'll go back to this one. So this term is going inside that one, so under root, and this is applicable for this, that will be IRMS by IDC whole square minus IDC square by IDC square, that will be 1. All right, and after plugging in the values of IDC and IRMS, that will be, we are evaluating for ripple factor. All right, it's a under root IRMS square upon IRMS upon IDC whole square. So what is IRMS? It's a IM by root 2, right, into IDC, that flips up, isn't it? So pi by 2IM whole square for this, and minus 1. All right, okay, whole square. Right, so guys, something gets cancelled over here, IM gets cancelled. All right, and that will be under root pi square from there upon, this will be 4 and 2, it's a 8 minus 1. So the resultant will be 0.48 something like that. I don't have a calculator with me, try that. All right, so what it says, it's a ripple factor IAC RMS by IDC is found out to be 0.48. check, it will be 0. I don't remember this decimal after that one. So what it says, IAC RMS is equal to 0.48 times IDC. It's only 0.48 times IDC. For a full wave rectifier, the ripple factor is much, 0.48. AC is only 0.48 times IDC. For a half wave rectifier, how much it is? For a half wave rectifier, it will be IAC RMS will be equal to 1.21 IDC. This RMS AC is more in half wave rectifier than AC in full wave rectifier. There is an improvement. All right. So see here, this value where it is, no comparison. All right. So these are the terms which will be asked in the exam point of view. Draw the circuit diagram of full wave rectifier explain that with the relevant waveform, and derive the expression for average current, RMS current, and therefrom evaluate the values of what was that, efficiency and ripple factor. Right. Conclusion once again, IDC to be evaluated, IRMS. All right. And what else? Efficiency, percentage efficiency that was found to be 80 point some decimal. All right. And ripple factor is found out to be 0.4 some, it may be 8, I guess. Right. These 4 important factors to be found out. Remember, we have current, and for a full wave rectifier, when we evaluate the RMS value of that current by √2. So whatever value, it's for the time being we had only 1 over here, so 1 time Im by √2. If we had something else, that would give us something else. Thanks for watching.